Welcome to this explainer. Look, we all know that back in ground school, hydraulic architecture is notoriously one of the most intimidating, dry topics you can study. I mean, it's often the system that gives pilots the absolute most anxiety right before an oral exam. But today, we're going to take the dense, highly technical data of the Embraer 190 and 195 hydraulic systems and translate it into a crystal clear, unforgettable mental model. If you're preparing for a typewriting or just really want to master the flight deck, you are in the exact right place. We are going to thoroughly explain the Embraer hydraulic systems 1 and 2 for pilots. Okay, here's our roadmap for today. We'll start with 1 point, main hydraulic power overview, then move into 2 point, inside hydraulic system 1, and 3 point, inside hydraulic system 2. After that, we'll cover 4 point, the power transfer unit, and finally wrap up with 5 point, abnormal system conditions. All right, let's dive right into Section 1, Main Hydraulic Power Overview, and specifically, the automation philosophy behind it. To really ground our mental model, check out this top-down schematic. It shows exactly how hydraulic power physically distributes throughout the whole aircraft. You can actually trace this logic during your pre-flight walk-around, kind of visualizing the lines running all the way from the engine-driven pumps down to those massive actuators in the wheel wells. Embraer designed these aircraft with an incredibly smart architecture. What this means for you sitting there on the left or right seat is that the system operates almost entirely automatically. It's specifically engineered to cope with abnormal conditions and component failures without needing your immediate manual intervention. It's essentially managing its own heartbeat, pushing pressurized, filtered, and temperature-controlled fluid to your vital flight control surfaces, the brakes, and the landing gear. But instead of just staring at the physical mechanics, we need to talk about how you actually interact with this beast. All of this complex mechanical data feeds directly into the cockpit. You've got continuous visual monitoring right there on the hydraulic synoptic page of your multifunction display, or MFD. And if anything, goes out of bounds, the crew alerting system, the CAS, is right there to generate messages, autotones, and flashing indicators. So the automation handles the execution, for sure, but real-time temperature, pressure, fluid quantity, and pump status are literally right at your fingertips to verify the aircraft is doing exactly what it's supposed to do. Moving on to Section 2, Inside Hydraulic System 1, which is going to be our baseline. Let's establish that baseline mental model. Notice the relationship between the two pumps here. On the left side, we've got the primary engine-driven pump, or EDP-1A, which is mechanically attached to the left engine's accessory gearbox. But look over at the right side. That's the electric AC motor-driven pump, or ACMP-1B. Now, in normal cruise flight, that electric pump is actually completely off. It acts as a backup, and it's automatically commanded on to supplement the engine pump only during critical phases where the aircraft demands high fluid flow, like primarily during takeoff and landing. But here is where the engineering gets truly brilliant. In a fantastic display of fail-safe redundancy, these systems are actually cross-wired. Imagine you lose the left engine right at V1. In some aircraft, losing an engine means losing a massive chunk of your hydraulic capabilities at literally the worst possible moment. But here, the backup electric pump for System 1, that ACMP-1B, is actually powered by the AC bus of the opposite engine, Engine 2. This means that even if you suffer a total mechanical failure of the left engine, there is no way you lose hydraulic System 1. The right engine's electrical power automatically spins up the left system's backup pump, keeping you perfectly pressurized to handle that emergency climb out. It's a real game changer. All right, Section 3, Inside Hydraulic System 2. Let's look at the mirror and the delta. We don't need to start from scratch to understand System 2, because mechanically speaking, it's largely a mirror image of System 1. However, the delta, the key difference, lies in its workload. While System 1 handles the outboard brakes and primarily left side components, just notice how System 2 is tasked with some seriously heavy lifting. It's responsible for the inboard brakes, the right thrust reverser, and crucially, the landing gear and nose wheel steering. System 2 is absolutely your runway survival system. Knowing this asymmetry is absolutely critical for your approach planning if you ever experience a failure on the right side of the aircraft. Because System 2 has to move massive physical actuators to deploy and retract the landing gear, it requires entirely different fluid dynamics. Therefore, its fluid reservoir has a significantly greater capacity than System 1. But it doesn't just hold more fluid. It's hydraulically pressurized by a mechanical piston. Now, why does this actually matter? Well, imagine you just commanded a gear retraction. That sequence requires a massive, sudden gulp of hydraulic fluid. If the reservoir was standard, the pump could suck it dry for a split second, causing cavitation. And trust me, you do not want destructive air bubbles in your lines. The mechanical piston forcibly pressurizes that larger fluid volume so the pump always has an instant, solid supply of fluid to grab onto. It is beefed up entirely to support that landing gear sequence. Which brings us to Section 4, the Power Transfer Unit, or PTU, the crucial bridge. This is an absolute favorite topic for check ride examiners, so pay attention. By definition, the PTU is a mechanical bridge. It consists of a hydraulic motor installed in System 1 that securely connects to and drives a hydraulic pump inside System 2. So the crucial takeaway here is that the PTU transfers mechanical power, not fluid. There is absolutely zero fluid mixing between the two systems. If you have a massive uncontained fluid leak in System 2, the PTU is not going to pump System 1's precious fluid overboard. It strictly transfers rotational energy across the gap. So why do we need this bridge in the first place? Well, remember how we just said System 2 controls the landing gear and steering? The PTU effectively exists as a mechanical savior for those critical components. Let's say you lose your right engine, or the engine-driven pump on the right side simply gives up. System 2 loses its primary pressure. Assuming your cockpit switch is in the normal auto position, the PTU instantly kicks in using System 1's power to ensure you can still safely operate your landing gear and steer the nose wheel once you get back on the pavement. Finally, Section 5, Abnormal System Conditions, focusing on the escalating alerts. Okay, we need to map out exactly how these systems respond when temperatures start to spike. Embraer engineered a brilliant rule of 3 for overheating, escalating step by step. Step 1, if fluid hits 100 degrees Celsius, you get a simple high-temp caution message. Step 2, things get much hotter. At 125 degrees Celsius, the system protects itself. A shutoff valve, or SOV, automatically actuates to physically isolate the engine-driven pump from that hot fluid. Step 3, critical heat. If the fluid reaches 145 degrees Celsius, you get a blaring hide overheat warning, and at this severe stage, the automation stops. It requires you to manually command the SOV closed through a guarded push button right on your overhead panel. Beyond just overheating, there's another critical abnormal scenario we really must discuss. What actually happens to the engine-driven pumps during an engine flameout? It's absolutely vital to consider the immense aerodynamic drag created by these hydraulic pumps when you're busy managing a critical engine out situation. Think about the drag for a second. Well, the engineers thought of this too. In the event of a flameout, the engine's computer, the FADEC, automatically commands the respective engine-driven pump to depressurize, or unload. By instantly removing that heavy hydraulic pressure demand, it drastically reduces the torque loads and internal friction on that failing engine spool. This piece of automation is literally a lifesaver, giving you the absolute best possible chance for a successful windmill restart in the air. So by understanding the logic behind these systems, from those cross-wired electrical backups that protect you at V1 to the mechanical genius of the PTU and those escalating thermal protections, you are now perfectly equipped to command the flight deck with real confidence. The Embraer handles the heavy lifting, but an informed pilot is the ultimate failsafe. Which leaves us with one final thought as you step into the simulator for your type rating. If the Embraer's hydraulic systems are this intuitive at saving themselves, are you fully prepared to let the automation do its job, or will you be fighting the aircraft?